This company, I was about to say Cold Quanta, because when it was started as Cold Quanta in 2007. It's a great name. A physicist came up with it. Dana Anderson, one of our founders. That's the company I joined. In November, we changed it to Inflection, which I think actually works pretty well. There are other names in the industry I don't think work so well, but I think that one's pretty good. I joined 14 months ago. I was maybe employee 146, and we're about 200 now. We have about 90 PhDs or other physicists or engineers, maybe a couple of stray mathematicians like me thrown in there, and generally doing very well. It's been a well-regarded, if somewhat quiet company. It has worked with the government for many, many years, many of the agencies in the government. In 2019, it got a $32 million Series A investment round, November 2019. And then 2 years later, last November, we announced a $110 million Series B funding round. And even though we were founded in Boulder, which I highlighted just for you, we also have offices in the UK. That's the second oldest. When we started our quantum computing program, we did that in Madison, Wisconsin. Professor Mark Safman, who's a professor at the university there. And as part of our Series B, we got $20 million from Breakthrough Victoria, which is a government-related VC fund around Melbourne, Australia. So I highlight this because there are 3 countries involved in these sites, right? We've got Australia, we've got the UK, and the US, which sort of spell AUKUS, right? And if you're looking at what's happening with geopolitical, technological alliances, these are the 3 main companies. You can enlarge this. You can throw in those. You can say Quad if we get Japan. If you take out Japan and you put in Canada and then New Zealand, you get 5 eyes, right? But the point being is that we are aligned internationally with the countries that are looking the most to do things with quantum, particularly as it relates to defense. But let's put it this way. We heard this morning there are many other countries that are doing phenomenal things, such as Finland, right? But from a geopolitical perspective, those are the 3, and that's how we made those choices. Now, these are the types of things we do. So let's start from the right, the components. What I don't mention, because we don't make them, is lasers. But we use lasers. We need lasers. We need small, cheap, very good lasers, please. But MOTS, magneto-optical traps, PICAs, photonically integrated sources. We deal typically with neutral atoms, cesium and rubidium, which you hit with lasers of certain frequencies, and they do marvelous things depending on what you're trying to do. That's where they come from. And then ultra-high vacuum cells. And this is an example. You'll see some larger pictures. I can never remember how to open this thing. This is a glass vapor cell. It's about 2.5 inches tall. Basically, you load that down with supercooled atoms, and then you shoot lasers at it, and different things happen, depending on how you have configured this. We make these. And as you will see, the world is going to need thousands upon thousands of these or smaller models in the future. But the significance here is that lasers come into play in many places, shepherding the atoms along so we can use things with them, right? Positioning the atoms, shooting the lasers at the atoms to have them respond in certain ways, depending on what we're building, right? And then ultimately, we can do various things, such as take photos of these things. But this is the heart of what we're talking about. I typically wouldn't be holding this if it was actually, in use, of course. Subsystems, atomic clocks. Clocks are an interesting thing to kind of talk about, because everybody knows what a clock is. Got a clock. Why do I need another clock? I need a more accurate clock. Well, okay, so I'm, only, 3 seconds late instead of 8 seconds late, right? Or something like this. This is not what we're really talking about. We're talking about these high-speed applications, and we're also talking about clocks that maintain their fidelity, how well they are keeping time for a long period of time. And that's what's different. Clocks have a very interesting history. Some of you may have read the book Longitude, which was about the creation of maritime clocks in the 1700s. It turns out, let's say you're in a wooden ship and you've just left England, all right? Well, it's not so hard to tell where you are north to south, latitude-wise, right? Because you can look at the sun, right, and do different measurements, and you know the date in their tables and things like this. But what's really hard to tell is your longitude, because that doesn't change. And so what used to happen was that ships would routinely arrive 3 weeks late because they were out there wandering around, right? Or even worse, they would crash into something. And so there was these huge prizes that were offered to people to come up with better clocks. And ultimately, they did, because before then, the method was called dead reckoning. So here's what dead reckoning is. You get a log, you tie a rope to it, you go to the front of the ship, you throw it in the water, and then you start walking backwards, going 1,001, 1,002, 1,003, and then you get to the back of the ship and say, well, that must be how fast I'm going. There are some inaccuracies built into this, as you can see. Well, that's still what we're doing. I mean, that's a basic principle, right? Because if I know the direction I'm going, and I know my speed, and I know my timing accurately, all those things accurately, I can tell where I am. And I don't need a GPS signal, right? Because GPS is not going to be around forever. Now, we also are working on quantum RF receivers, radio frequency receivers, to replace some of the very big antennas, to expand the RF spectrum, the usable RF spectrum. We have tools for actually doing things. I'll show you a little bit about our sensor design platform. We're going to talk much more about quantum computing. And then on top of all this, working up the stack, how do we use these things for practical problems? Now, our technology has gotten pretty far away. This is astronaut Christina Cook. She is one of the 3 that has been chosen for the Artemis II flyby mission for the moon. And she was the mission specialist for the Cold Atom Lab sent up by JPL. There have been 2 versions, and they both have cold quanta technology at the core. So when people ask us, well, you know, how robust is our technology? Well, we put it on a rocket and sent it into space twice, and it seems to work pretty well, okay? Now, okay, that's an existence proof. Ultimately, we're going to need that in satellites and other sorts of things too. But this is an example of maybe the quiet but long-standing systematic work that neutral atom technology with photonics has been doing over the last few years. Did you know there were lasers on the International Space Station doing weird things to weird atoms somewhere in the middle of the periodic table, right? This is an example. In terms of what we can do with this, we're focusing on 2 markets principally to begin with. We're looking at several, but atomic clocks, because it's going to be a volume play. The idea is to make them smaller and smaller and more ubiquitous. And as I mentioned, radio frequency sensing. If you look at a cell phone tower, there are a variety of things up there. Sometimes you see things that look like big horns, right? Other times you see these very large boxes. They're often kind of beige. The size of that receiver is related to the frequency of the radio frequency at which it can receive. So they can be smaller and larger. If you look at a battleship, military battleship, there are dozens upon dozens of different sized receivers for the different frequencies they use in the military. Ultimately, what we're going to do, and that's what's shown over there, is maybe about 4 times the thickness of this, but this size. It will be programmable, and you can set it to any frequency. And we'll have far greater sensitivity, so you can be assigned a smaller part of the frequency, and you can push out further on the sides, closer to 0, closer to 20 gigahertz as well. So putting 50 of these up, as opposed to, right, 50 very large things, means we can find far more uses for them. And ultimately, the dream is to figure out how to put them in something as small as an actual cell phone. That's a long ways off, just to be clear. So the goal is to make these things smaller and smaller. In terms of the clocks where we're going, we have called these ticker. Yes, we do have this problem, like much of the quantum industry. If that word has a C or a K in it, it's not going to last long, right? The idea is to go to rack-mounted, very high accuracy, very stable atomic clocks. In the first generation, within the next 2 to 3 years, followed in about the same time period by generation 2. These will be about this big, let's say, maybe a little smaller. And then ultimately, the idea is to get them far, far smaller. But at any of the generation 1 or generation 2, those are very suitable for data centers, which now have just a handful of atomic clocks. You can ultimately have far, far more of them, and you can start to deploy, especially around the middle generation, far more broadly cell phone towers, every ship, so forth. When you get to this point over here, and again, we're not doing that without you. I keep putting all this pressure on you. But this is what's going to require PICs, right? Inexpensive, highly accurate, stable PICs. That's the only thing. And if we don't get those from you, right, that generation 3 is never going to happen, or it's going to be extended. So, but that's what we're looking for. And so if you look higher up the stack of what is being done with photonics, these are the types of applications. This is the next level hardware. And then we can walk up and say, well, why do I need an atomic clock? What application? What solution is that part of? And so forth, and things like this.